بسم الله الرحمن الرحيم. خلينا اليوم we start with chapter 6 which is about momentum equation. What is meant by momentum equation? We mean the Newton's second law of motion, which is specifically F تساوي ma. This is in a system form. We need to transform it into a Lorentzian form or field point of view so that we can use it for a fluid flow analysis. Okay, in general, we can write the summation of forces acting on a particle or a body of mass m times acceleration. This is Newton's second law. Now we want to do a few things. We write again summation of forces تساوي ma, but we recognize that a, of course it's a vector, it's actually equal the derivative of velocity in this manner. Because in our case the body mass is constant, we can insert it inside the derivative, so it becomes mass in this manner. Now we recognize this term to be the linear momentum, يعني زخم تساوي mv. Obviously this is extensive property because it depends on the mass. We can make it intensive by writing or by dividing by mass. Remember, this is not the pressure. This is usually we use it for a symbol for momentum, زخم. Now we can go back to the Reynolds transport theorem, which was developed in chapter 5, to use it to transform Newton's second law into a form that can be used in the fluid flow analysis. Okay, in this equation, capital B in our case, which is the linear momentum, which is mv, the small capital B, which is the velocity. So wherever we see small b, we put in its place velocity as seen, and then we can say the time rate of change of momentum, linear momentum, is equal to these two terms. But then again, we recognize that this term is equal to actually the summation of forces, so we drop it and we use instead of it the summation of forces equal the time rate of change of linear momentum inside the control volume plus the rate of momentum leaving the control surface of the control volume. Okay, we want to look at a specific case which very common in the fluid mechanics or in this solution. Suppose we have one inlet. Now we recognize this area is a vector normal out. Suppose the velocity is uniform in this case, meaning as a constant velocity. Suppose also at the exit the area of course will be out normal. Also the velocity, assume it has a constant velocity or uniform conditions. In this case, when we have uniform velocity at the inlet and the exit, we can take the velocity out of the integration, and then we're left with density times velocity dot dA. We recognize this term to be the mass flow rate. So upon this, we can decompose this term v rho v dot dA into two terms. Because v is uniform, we can take it out, so it will become the summation of mass flow rate v at out is positive, and also negative m dot v at the inlet. So in general, under uniform conditions or uniform velocity, we can transform the equation into this form. Now let's go back to the equation one more time. This is in words, as we said before, the summation of forces acting on the control volume equal to the time rate of change of linear momentum inside the control volume plus the net outflow rate of momentum leaving the control volume through the control surfaces or the surface. Now we have to go back to this equation again and remember an important point, because Newton's second law required that the velocity be with respect to inertial frame of reference, that is non-accelerating frame of reference. So wherever we have velocity entered in the Reynolds transport theorem, it has also to follow the same rule. Specifically, this velocity and this velocity must be measured with respect to inertial frame of reference. Whereas this velocity, which comes from the Reynolds transport theorem, has to be only with respect to the control surfaces. Because this is a vector equation, we can decompose it into x, y, z. So for example, in the x direction, we say the summation of forces acting in the x direction equal to the time rate of change of momentum in the x direction inside the control volume, z, the linear momentum in the x direction leaving the control volume, minus the flux of momentum entering the control volume through the control surface, and the same thing true for the rest of them. In solving the momentum equation, we have to follow these steps, the four steps. First of all, we have to identify and draw the control volume. It's meaningless to speak of momentum leaving the control volume or momentum entering the control volume, which control volume we are talking about. So at least we have to envision the boundaries or the surfaces of this control volume. Second, we have to draw the control coordinate system. Again, because we're talking about a vector equation that can be decomposed into x, y, z, for example. So we have to identify our coordinate system. And also we have to identify where mass enter and leaves the control volume. Also we have to identify the forces acting on the control volume. We need to remember there are two kinds of forces. We have body forces, which are like gravity, which acts at every element of the body without being in contact with the surface of the earth. And we have surface forces which require contact with the control volume, like friction forces. Okay, let's take this example, 6.1. We have a toy rocket, ألعاب نارية. Its mass 40 gram. We need to measure or evaluate its thrust. We have fixed it to a wall by a beam. Under firing, we have a gas jet coming out of it, as you see. We remember that a jet is an organized fluid that has certain velocity, and usually it travels in atmospheric air, so the pressure around it will always be atmospheric pressure. Under these conditions, we have the gases leaving the rocket at speed of 450 meters per second downward. Its density is 0.5 kilogram per cubic meter, and its circular jet with diameter 1 centimeter. Under these conditions, we need to evaluate the force FB acting on the beam. يعني the rocket tries to go up بينما الbeam holds it down. Okay, we need to remember the steps in solving this problem. First of all, we have to draw and identify the control volume, so we have drawn it like this. This will come with as you do more problems, you will gain the experience on dealing with control volume. Two, we have to identify or draw the coordinate system. In this case, we have only one coordinate, which is the y-axis or the elevation. We're not concerned with the other directions. ثلاث, we have to identify where mass enters and mass leaves. There's no inlet to this control volume. We only have mass leaving the control volume. Four, we have to identify the forces acting on the control volume. In this case, obviously, we have the weight downward, and also we have the force exerted by the beam on the control volume, which is trying to hold it in a place. Okay, how we solve this problem? We could go back to our original equation, which says the summation of forces equal time rate of change of momentum inside the control volume plus under uniform conditions. We have decomposed the momentum of flux through the surfaces into two terms as seen here. Okay, we're interested in y direction. Okay, what are the forces acting on this control volume? We have weight and FB. Both are acting in the negative y direction, so we write minus W minus FB. In most cases, we'll take steady. Okay, we have no mass entering, so this is zero. We're left only one stream fluid, which is basically m dot and the FG. Of course, and instead of the FG, we can write the magnitude of the velocity, which is, notice it's minus 450 downward. Okay, it's minus because the velocity here is in the negative direction. And then we only need to evaluate the m dot in this case. If we have the control volume as drawn, notice that the velocity is downward. Notice the area is out normal in this direction. So الزاوية بيناتهم is 0. So this leaves us with rho v dot A being positive. Density is given to us as 0.5 kilogram per cubic meter. Velocity is given to us as 450 meter per second. Notice in this case, we don't take this as negative. We worry about the entire sign of the entire term. And the area is بهالشكل هذا. We observe that meter squared times meter مع meter cubed. So we're left with kilogram per second, which is the massive flow rate. Or we recognize, as he puts it, that m dot is rho va minus 450, which is the velocity. So this leaves us with minus rho v squared a. So in this case, we have minus W minus FB, so minus rho V squared A, which implies that FB equal rho V squared A as he puts it in this form. Okay, let's take another example. In this case, we have a cart, عربة, is placed on a scale محطوطة على ميزان, and also this cart is held by a cable to the wall, so to stop it from moving horizontally. Okay, bear with me in this problem. We have the units in British units or British system. Concrete is being poured from a hose in this direction, making 60 degrees from the horizon. This, as a jet, has a cross-sectional area of 1 foot square. the speed of it in this direction is 10 feet per second. At the instance shown, the weight of the cart and the concrete inside is 800 pound force. المطلوب we want to determine the tension in the cable and also the reading by the scale. Okay, how we solve this problem? As we said before, we need to solve it in 4 steps. Okay, let's look at it. First of all, we have to identify and draw the control volume. We have drawn it around the cart because we are interested in the its weight, and we are interested in the tension. So it's obvious that we have included everything in the cart as shown. Okay, we have a fluid entering, we have no fluid leaving. The forces acting on this control volume, we have tension, always tension pulls, we have the weight of this cart, and also we have the normal force exerted by the scale on the cart. Okay, now we apply this into 2 directions. So we have said we have x direction and we have the elevation direction. Okay, then we take our general momentum equation and we decompose it one time in the x direction and the other time in the, as seen here, in the z direction. Okay, as we said, we will neglect any unsteadiness in the problem, so we will assume this is 0. We have no mass leaving, so this is 0. So in the x direction, we end up with the summation of forces acting on the control volume, so the negative of the flux of momentum entering the control volume. Okay, if we want to further show this problem, so we have the control volume, we have the tension, there is no other forces acting on this control volume, and remember we have the x and z elevation. The jet is coming at this velocity, at this direction, making 60 degrees as if, and in this manner. Okay, so when we apply it in the x direction, we have the summation of forces equal to minus tension. So the tension is negative again. This is the only force acting in the x direction. Again, we will always assume steady unless otherwise is stated. There is no mass leaving, no momentum leaving. We only have one stream of momentum entering. So we have m dot. Now we have to look at the velocity. We have to take it in the x direction, so we have to decompose this velocity into 2 directions. One in the z and the other one in the x direction. This component is the v cosine 60. So this, now when we compute the m dot, we have to recognize this rho VA. Now, in this manner, so we say the density, which is given to us as 150 pound mass per cubic foot. The velocity is given to us as 10 feet per second. The area is given to us as 1 foot squared. So again, we observe that foot squared, foot cubed, they cancel out. We end up with pound mass per second, which is equal to 1,500 pound mass per second. Okay, so tension, canceling out the minus sign, is 1,500 pound mass per second, multiplied by the velocity, which is 10 feet per second, multiplied by the cosine of 60, which is half, so we end up with pound mass foot over second squared. Now to transfer this into pound force, we have to divide by 32.2, so to get the number in pound force. Okay, so here's the tension equal the, as we have seen in this equation. In the elevation direction, same thing. We have to go back to our problem. We have weight, we have normal. So the forces in the z direction are weight downward, normal up. We have, as we said, always assume it's steady. There is no mass leaving, only entering the same number m dot. Now we have, this is the component velocity in the z direction, so it will be sine v sine 60, but we recognize this is in the negative z direction, so we have to place a negative here. So in this case, it will lead to that normal is equal to weight plus this magnitude, which is due to the momentum change or due to the momentum flux. Again, we have to pay attention to the units when we talk about the British system. In your case, as we said many times, you don't have to worry about the British system of units. You're only asked during the examination using the SI system. Let's continue. Nozzles. What are nozzles? Nozzles are devices or fluid devices that they accelerate the fluid. Okay, to understand their function, let's consider this example. In this case, we have a nozzle connected to a pipe system. The fluid here has a pressure, and the fluid is ejected to the outside atmospheric pressure. The fluid at station 1 is given to us as 105 kilopascal absolute, whereas the atmospheric pressure is 101.3 kilopascal absolute. We're given the diameter here to be 6 millimeters, whereas at the exit we're given it to be as 1 millimeter. المطلوب هون find the airspeed of the exit of the nozzle and the force required to hold the nozzle stationary, يعني ثابت. And we're given the density being 1.22 kilogram per cubic meter. جماعة, in this case, you will see that we will be using the three equations to solve this problem. First of all, let's draw the control volume as he's done it in this case. Okay, so in our case we have the nozzle, it's held by the flanges, and we draw our control volume in this manner. Okay, recognize that the fluid here has a pressure force, which is the pressure free area, and here also we have a pressure force, which is the atmospheric pressure. We will neglect its weight. Also we have fluid coming in, we have a fluid leaving in this manner. So basically we are interested only in the x direction, so we have drawn the control volume, identify the coordinate that we need, which is the x direction. Mass enters and mass leaves, and we have the forces acting on it here mainly in the x direction, which is the force of the flange to hold it stationary in this manner, in addition to the pressure forces given as P1A1 هنا given as P2 A2, which is, as we drawn it, is equal to A1 in this manner. Okay, if we simplify our equation, the momentum equation, again let's write it one more time. in this manner. Okay, we will assume steady. The forces acting on this control volume are P1 A1 minus P2, which is the atmospheric, A2 and A1 are the same, minus the F flange equal to 0 steady, mass leaving V out, it's all in the x direction, minus mass entering Vn. Okay, this results from the momentum equation. We recognize that because A1, A2 are the same as we drawn it, that P1 minus P2 is the gauge pressure at the inlet. If we take that the gauge pressure at the inlet, then the gauge pressure here is equal to 0. And this is what we will use from now on. When we're dealing with these problems, we only consider the gauge pressure. So mainly P1 gauge A1 minus F flange in this manner. Okay, now under steady state condition for the mass balance, mass entering equal mass leaving. So we recognize that m dot outlet so m dot inlet. So we can take it out, and then we end up V out minus V inlet. Okay, now what's the m dot? We can recognize that m dot is equal to rho 1 V1 A1, and also it's equal rho 2 V2 A2. But we don't have the velocity V1, so how do we get it? Okay, we go back to the Bernoulli equation and we say P1 plus gamma Z1 plus half rho V1 squared equal to P2 plus gamma Z2 plus half rho V2 squared. So here we have an equation which implies that V1 A1 is V2 A2. That's one equation. And then we have another equation here. Now observe that the elevation is not important. In this equation, P1 and P2 are given. So we have two unknowns, two equations, we can solve them easily. Okay. So again, we obtain this equation from the momentum equation. We obtain this equation from the mass balance. We obtain this equation from the Bernoulli equation. So we have three principles. So we want to use the mass balance and the Bernoulli equation to obtain a form for the velocity. Meaning, or specifically, we have P1 minus P2, which both are given, equal to half rho V2 squared minus V1 squared. But we recognize from this equation that V1 is equal to V2 A2 over A1, or we can say V2 A2 عبارة عن باي على 4 diameter square, which is 0.011 square millimeter. Excuse me for a second. Let's use a different sheet. So from the Bernoulli equation, we recognize that P1 minus P2 equal to half rho V2 squared minus V1 squared. Now we use the mass balance to say that V1 equal V2 A2 over A1, which is V2 A2 is pi على 4 1 millimeter squared converted to meter over pi على 4.006 squared بهالشكل هذا, which implies that V1 equal V2 1 على 6 الكل سكوير. So if again substitute v for v1 its value, we end up with p1 minus p2 equal half rho v2 squared minus v2 squared 1 over 6 squared idiot to the fourth power in this manner. So now in this equation we can solve for v2 by knowing p1 and p2 and given the density in this manner. So we have solved for v2. If we have solved for v2, we can find v1 from this equation, and then we go again to the momentum equation to solve for the force required to hold the flange or the nozzle, stationary. يا جماعة, when we apply this equation, we have to recognize, let's go back to the other page, we have to recognize that when we use meter per second, kilogram per second, this will give us a Newton. But if we use here kilopascal for the pressure, it will give us kilonewton. So either we divide by 1,000 or multiply this by 1,000 to make the units consistent. Okay. Here, as we said, how we solve for V2, and then we solve for V1, as we said before, and then here how we found the force اللي هي necessary to make the flange stationary أو ثابت. Notice here he multiplied the gauge pressure by 1,000 to change the units into Newton from kilo in Newton. طيب يا جماعة نكمل veins. What we mean by veins, a vein is a component زي ما حكى هون structural component, يعني جزء من الديفايس اللي احنا we're talking about. وبالعادة هذول they are very thin. We use them, نستخدمهم على أساس نحرف مسار الجت, مسار الفلويد, to turn the fluid jet direction. Their uses, استخداماتهم, نستخدمهم as blade in a turbine or compressor, or for example as a sail in a ship, الأشرع تبعات السفن. And also we use them as a thrust reverser on an aircraft, على أساس إنه to slow down the aircraft when landing في حالة الهبوط. طيب, هون we have a simple schematic for a vein seen being impacted by a jet, fluid jet, and this jet will split into two directions زي ما انتم شايفين أمامكم. Usually in these veins we neglect pressure changes due to elevation because they are very small, so the elevation pressure difference is negligible. And also under the ideal condition we have V1 equal V2 equal V3. This can be easily shown if we apply the Bernoulli equation between stream 1 and stream 2. Applying Bernoulli equation, which is in this form, recognizes that elevation is insignificant. Also, this is a jet being exposed to the atmospheric at most cases, so we have gauge pressure equal to 0, gauge pressure equal to 0, this equal to this one, so we're left with this term equal to this term. And also we typically assume that the density variation is insignificant or incompressible, either fluid or flow, so we end up with being rho cancel out, we end up with V1 equal V2. Same thing we can do as we did for V1 and V2, we can do for V1 and V3 and show that V1 equal V3. So we end up with V1 equals to V2 equals to V3. Under real condition, however, always V2 and V3 are less than V1, and not necessarily that V2 will equal to V3. Okay, let's take this example to show how they work. We have a water jet is deflected by 60 degrees by a stationary vane from the horizon. The incoming jet has a speed of 30 meter per second والdiameter تبعه circular اللي هو عبارة عن 3 سنتي. Find the force exerted by the jet on the vane. We know from Newton's first law that this jet, to turn its direction, there must be a force acting on it. In turn, the force acting on the jet must equal to the force acting on the vane itself. For every action there is a reaction. Okay, how we solve this problem? First, we draw a control volume as shown here. Okay, and then we apply our momentum equation for this control volume, one time in the x direction and the second time in the y direction. Okay, let's write it again, the momentum equation, to remember it. We have summation of forces equal to time rate of change of control volume as of momentum inside the control volume plus momentum leaving minus momentum entering. Okay, as we said, we will assume steady. Alright, we need to apply it in the x direction. What are the forces acting at this control volume in the x direction? Okay, kg pressure equal to 0, kg pressure equal to 0. We will neglect the weight, so there is no forces at the inlet, at the exit, no weight. We're left with the force which is exerted by this support. Upon its decomposition, it will be Fx. So in this, it will be minus Fx. It's minus because acting in the x direction, equal to 0. Now we have mass leaving, but when we say the velocity, the jet is coming in this direction. When it leaves at this, and only we need to consider the x component of it, which is v cosine 60. Again, it's acting in the positive direction in this manner. Okay, for m dot is our equation rho va. Density for water is 1000 kilogram per cubic meter. Velocity is given to us as 30 meter per second, multiplied by the area, which is the jet, O3 squared pi على 4 meter squared. Okay, or we can go back and say minus Fx equals 0 plus rho a v squared cosine 60. This is it. Because we have obtained I apologize. Also, we have the minus m dot. Now, all the velocity entering in the x direction. So we have minus, once again, rho a v squared in this manner. So we end up with rho a v squared cosine 60 minus 1 to 7 minus f of x. again momentum leaving, momentum entering. We do have one inlet, one exit as seen here. Okay, so this is our equation اللي هي solved. In the y direction, we have also to solve it. Here we have no component in the y direction. Here we only have one component in the y direction. So in this case, we go back to the figure. We have minus Fy equal to leaving, there's no y component, so 0 steady, 0 leaving, minus m dot multiplied by this component. Now we need to put minus v sine 60. So again, this indicates that the jet will be acting on the beam in the y direction because we have negative, this is موجب, so Fy تساوي سالب rho v squared area sine 60 in this manner. Okay. Okay, so the direction of the force that we have assumed for the y component, it will be in the other direction, which is mainly upward, because we have assumed it will be downward, so it will be actually up. Whereas for the x component, we recognize that cosine 60 is less than 1, so this is negative. So that means the force will be موجب, indicating that the direction we have assumed for the x component is correct. Okay, let's take another example. Here we have what we call an axisymmetric vein. Let's look at this one again. We have an incident jet coming to this axisymmetric vein. The jet has a density rho, speed v, area a, leaving at an angle beta as seen here. Find the force required to hold the vein stationary. This vein, it looks like a plate or like a lemon, to squeeze lemon out, which is the عصارة الليمون بهالشكل هذا. If I want to draw it, maybe I'm not a good artist. So the jet is coming this way, and when it leaves in all directions. So it's coming in this direction, and it leaves in all directions. Okay, so recognizing that we have one inlet and we have one exit, but this exit is around the المحيط اللي هو periphery of this vein. Okay, so we have one inlet, one exit. If we recognize this, then the problem is easily solved. So again, we choose a control volume. We want only a force in the x direction. The weight, we will neglect it. And then we apply our momentum equation اللي هي summation of forces equal v rho dv plus momentum leaving ناقص momentum entering بهالشكل هذا. Steady. Summation of forces, we have F because we assume this acting in the negative x direction, equals 0. We recognize that the m dot is the same for the exit and the inlet. The velocity it's leaving at an angle beta. So we take only this component. So we say v minus cosine beta, minus because it's acting in the negative direction, minus, this is the leading, minus from this the rule, and then we have the velocity, all of it is coming in this direction. Okay, we can say rho VA, and then we take also this V out, so it will be squared, and then we are left with minus cosine beta minus 1, or minus F equal to rho V squared area 1 plus cosine beta. Okay, all right.